that graphene is 30 times more sensitive than silicon, but they consume 1,000 times less energy.
Technology is advancing at an exponential rate, with new breakthroughs and innovations all the time. But it's not every day a new material comes along with the potential to create a huge difference.
When graphene was first discovered in 2004, we were told the so-called supermaterial would change the world. But fast forward to the present day, and has the revolution happened yet? Well, I've come to a lab near Cambridge, one of the world's first companies mass producing graphene-based electronics, to see for myself.
Professor Sir Colin Humphreys is the co-founder and chief scientific officer of Paragraf, a company designed around graphene.
Its mechanical properties are being exploited, and so it's being added to concrete and meant to make it stronger, to tarmacs in road, to running shoes, to tennis rackets, to a lot of products like this. And it has made inroads into these other areas, but the real promise of faster transistors just hasn't happened, and faster computers and faster mobile phones, better energy consumption. None of these had happened until we got involved.
Graphene was first isolated in 2004 by scientists Professor Sir Andrei Geim and Professor Sir Konstantin Novoselov at the University of Manchester during a chance Friday afternoon experiment using the so-called sticky tape method. Carbon comes in many forms, called allotropes, the most well-known being diamond and graphite. In a diamond, each carbon atom is connected to 4 other carbon atoms. It's this extremely strong arrangement that makes diamond one of the hardest known materials. In graphite, each atom is linked to 3 others in layers of hexagonal shapes. The bonds within the hexagonal sheets are strong, but each layer is only weakly attracted to the next, which allows the layers to slip by one another. If you peel away layers of graphite, you end up with a monolayer honeycomb lattice of graphene, which is a single atom thick, which is why it's known as a 2-dimensional material.
It's very strong, it's transparent, it's the best electrical conductor in the world, it's a very good thermal conductor, it's flexible, and all these properties are in a single material, and so people are really excited about it.
But there was a problem to overcome before graphene could be used in electronics. In 2015, Professor Humphreys was working on another material in Cambridge when a PhD student asked to focus on graphene.
I give her a piece of gallium nitride, and I send her up to Manchester to meet the Nobel Prize winner there. And he gives her a little plastic box, and he says, inside this box there's a piece of graphene, and what I want you to do, he said, is to make a transistor by hand by putting this graphene on top of the gallium nitride and putting some contacts on. And she looks in the box and she says, there's nothing there, right? And he said, that's because it's transparent, right? And she spends a month trying to find this thing by feel, as it were, with tweezers, right? and then assemble by hand, and she cannot do it. And so I then get on the phone to Kostya Novoselov, this Nobel Prize winner, and I say, Kostya, I supply some gallium nitride, which is 2 inches in diameter. Please can you supply a piece of graphene, which is 2 inches in diameter, because even though it's transparent, there's a chance she can assemble a transistor by hand. And he roars with laughter. And I say, Kostya, this on the end of the phone, I say, Kostya, why are you laughing? And he said, because device quality graphene, 2 inches in diameter, doesn't exist anywhere in the world. And because I hadn't worked in graphene before, I didn't know that. And he said, there's just the tiny flakes.
So Professor Humphreys set his research group a task to find a new way of making graphene.
And then one of my senior postdocs, who's now the CEO of this company, Paragraf, he came to me after about a month, and he said, Colin, I've had an idea of a new way of making graphene, and we made this large area graphene, and then we made the first prototype, what's called a Hall effect sensor, which Paragraf is then manufacturing. But for very little money, and I happened to have the right equipment and the right people at the right time, and we did this work.
The two postdocs were Simon Thomas, now the CEO of Paragraf, and Ivor Guiney, the group's technical director. Paragraf is one of the world's first companies to mass produce graphene-based electronic devices.
Oh wow, this is an impressive bit of kit. What's happening here?
So we're just unloading the graphene samples here. So each of those 2-inch wafers has a single monolayer of graphene on it, and this is how it looks in its as deposited form.
That's the graphene in each wafer?
Each on each substrate, yeah. There are 31 wafers in here, and you can get over 1,000 devices easily on a 2-inch wafer like this. So we're talking high numbers. Some of our reactors will be used for kind of high throughput, high uniformity, more production grade things, and some of them will be used more for research and development, so looking at smaller quantities of devices and tailoring them to new applications.
And what's the process? How does that happen?
Here we can see the fresh substrates being loaded in, ready to be deposited with the graphene. So they'll be loaded into here, and then it will be closed down, and once it's closed down, there'll be a series of conditions that are needed for the process to take place. So basically some chemical precursors will enter the environment with the substrates, and the reactions that go on in there is what leads to the graphene being deposited.
The exact process is a secret, but it works something like this. A variety of gases containing carbon are injected into a chamber. The gases mix when they hit a substrate, which has been heated to over 1,000 degrees Celsius. Hydrogen is released and the carbon atoms skate around until they find each other and link in a honeycomb array, leaving a layer of high purity graphene on the wafer.
What makes this method unique?
When you grow directly on your chosen substrate instead of on something else and then transferring the graphene later, you can keep that graphene more intact and more protected and less contaminated by the different processing steps that you would need to move it around. Being able to grow on larger and larger areas of substrate will enable us to scale up and make millions of devices at a time.
The first electronic device Paragraf is producing is a magnetic field sensor, which works on what's known as the Hall effect.
So here you can see an illustration of the processing steps involved to take graphene from its on-wafer state to a finished device that can be used in different applications. So here we can see a wafer much like what we saw in the reactor, where there's a single layer of carbon atoms across that whole 2-inch wafer. So the graphene goes through various stages, including adding other materials that are needed for the device structure. We need to be able to contact to that device, so that's where the metallization step comes in. And you can see some contacts have been added there. They connect the graphene to the rest of the system. The devices are then singulated to give individual die with one device on each one. And these are then placed into protective packaging. And again, this would all be connected with wire bonds so that you can measure with the device.
And what does the visuals here on the screen show us?
So this animation here shows how the Hall effect works in our sensor. So if you imagine that red material there is the graphene, and we have a current traveling in one direction through the material. When that goes into a magnetic field, as you can see coming in here, the moving charge carriers are all experiencing a force that deflects them over to one side of the material. So that causes lots of charge on one side and less charge on the other side. So we measure that potential difference across the device. That's shown by the voltmeter moving here. And the amount of voltage that we measure from that potential difference depends on the field strength and the sensitivity of our material. So we can use a device where we know the sensitivity to work out the strength of the magnetic field, and you could move it around or use lots of different devices to map a field effectively.
How is this being used out there in the real world?
So you could use the sensor in a variety of applications where you need to either detect a magnetic field, and that could be something really simple like whether a door is open or closed, and you can use that in things like electric car batteries to work out where there are defects and prevent fires from happening. Or it could be used to map a very precise magnetic field, such as you might need for medical applications or high-level physics research.
What are the advantages of using graphene in these devices compared to the materials that are currently more widely used?
Graphene has loads of really beneficial properties for using in a Hall sensor. So the material itself is really sensitive to magnetic fields, which means that we get a really good, strong response, and we can measure the fields very precisely. The fact that graphene is only a single layer of atoms means that it's not experiencing any through thickness effects in the material, so you get a much cleaner measurement of that magnetic field. And graphene devices can also consume much less power, so in the move towards more energy efficient devices, graphene could really play a role with its integration.
Another advantage is that it can be used at very low temperatures, which makes it ideal for use in machines like MRI scanners and quantum computers. Once the sensor has been assembled, they're checked here and then tested under liquid nitrogen. The Hall sensors use a very small cross of graphene between 4 metal contacts, as seen here under a microscope. Paragraf is also producing another type of sensor.
A very exciting product being made here is a biosensor. Graphene biosensor is very, very fast and can give you rapid results. And we believe that you can distinguish between viruses and bacteria. You can distinguish other different types of bacteria, different types of viruses. So there's something called sepsis, which kills lots of people. And to detect sepsis at the moment, you have to take a swab, say saliva, and you culture it, you culture the bacteria or viruses there, and you then do analysis in an electron microscope, and that takes 24 to 48 hours. We believe with a graphene biosensor, you could determine that in maybe 10 or 20 minutes. So it's going to change the world, it's going to save lives.
Dr. Martin Tyler is quality checking a batch of new biosensors.
This is what the wafers look like when they come out of our fab. We produce 32 devices on a 2-inch wafer. That's kind of one device there. So then that's another one. So it's 6 rows and 6 columns, 7. So after this, it will get sent through a cleaving process to singulate the dies. So they then get attached to a PCB. So that's a single device there. Wire bonded out to these tracks. And then that whole chip and wire bonded assembly gets coated in an epoxy, mainly to protect the wire bonds, but with the added benefit that it also produces this kind of cavity or well that we can leave liquid in during our tests.
What are the benefits of using graphene in this way?
So traditionally in these sort of devices you'd be using 3D bulk materials, and one of the key improvements you get from graphene is that because it's a 2D material, it's essentially all surface area. So any changes to the surface is really a change to the entirety of the material. So you get an enhanced sensitivity because of that.
This enhanced sensitivity allows for faster detection than traditional devices. It's also possible to detect more than one virus or bacteria on a single device. Research is still underway to incorporate graphene into computers, which should make them much faster. But there is another advantage too.
It turns out that graphene is extremely energy efficient, and these magnetic sensors I was just talking about before, they're 30 times more sensitive than silicon, but they consume 1,000 times less energy. And so if we can make transistors, as in computers, from graphene and from other two-dimensional materials, then they'll save a lot of energy.
The reason graphene consumes such a low amount of energy is due to electricity flowing through a layer of conduction electrons which exist above and below its 2D layer of carbon atoms, and not inside the material itself, as would be the case in a 3D structure.
And when graphene was discovered, it was the only material in the world in which the conduction electrons moved on the surface. Since then, we found another set of two-dimensional materials, and theoretically, I think 5,000 are now being found in theory, and only a few hundred are being made, of these special materials where the conduction is just on the surface, and we expect all of those will be low energy consumption materials. So if you look at, say, what's going to be the future of Paragraf and the future of graphene is to look at other two materials as well, because for certain sorts of transistors, they may be even better than graphene. And so that's a huge prize for two-dimensional materials and may help us save net zero.
Graphene was the first example of a 2D material in the real world. Many more have since been discovered, such as boraphenene, silicene, phosphorine, goldine and plumine, which each have their own set of unique properties. And there are many more yet to be found. 20 years since graphene was discovered, the so-called wonder material is slowly starting to live up to the original hype. Manchester has become the UK's home of graphene and 2D materials research, opening the National Graphene Institute in 2015 and the Graphene Engineering Innovation Centre, known as the GEEK, in 2018. John Whitaker is the group's engineering director.
Where are we and what is the work you're doing here?
So this building is the Graphene Engineering and Innovation Centre. It's heavily focused on industrial applications. So we're a part of the University of Manchester. We work with our academic colleagues. We say we are industry-led here. So industry dictates the work that we do in here. But we also respect the huge amount of graphene research and 2D material research at the University of Manchester, of which we get a constant academic feed, and this is quite important for industry going forward. So we use graphene as one example. Isolated 20 years ago, National Graphene Institute 10 years ago, has now been feeding into applications. We've set up the pipeline here at Manchester to do that with other 2D materials. The reason why the Graphene Engineering and Innovation Centre is unique throughout the world is that it focuses on that application, that proof of concept to the prototype, but working with the supply chain and the regulators to ease the adoption.
Here we are speaking 20 years on. There was much said at the time about the potential for this material to completely revolutionise the way we live and work. Has that happened? Has it lived up to the hype?
Yes, it has. Certainly in the last 5 years, we've been delivering graphene and 2D materials technologies to a huge wide range of industrial applications.
We're now reaching the stage where real applications and products are starting to emerge.
When a new material kind of comes along that can add value, industry has to verify the data. So it's got to be safe to use, got to be safe to employ, safe to work with, and we're going through those application processes now. It's called regulatory compliance.
Apart from electronics, graphene is mostly incorporated into another material to lighten and strengthen it. It's been used in building materials such as concrete, consumer products such as plastic bottles and in trainers, and also in the automotive and aerospace industries. An estimated 40 million products now contain graphene. One of the big obstacles in bringing it to market was the scalability of graphene production. The good thing is only a small amount is needed for most products.
One example of graphene I like is 1 gram of graphene will cover a surface area of over 2,600 square metres.
That's roughly the size of 10 tennis courts.
You only need a very, very small amount of graphene in a system, for example like a polymer or a battery system, to have a significant effect, and that's what we find in applications today.
The Geek focuses on working with industry and has 6 application laboratories. One area it's hoped graphene can make a difference is sustainability. Dr. Nikki Sevjani is the Energy Applications Manager.
When you think about graphene first being discovered back in 2004, its use in better battery life was one of the big properties we heard being talked about. Has that really happened?
So this is the biggest challenge at the moment. With the world pushing away from fossil fuels, battery technology has been developed through an astonishing speed. The problem is implementing something as graphene, which was still not well understood at the time, was difficult. Now that graphene has become a more established material, there is now a clearer drive to get graphene materials into battery technology.
How is graphene actually used in these batteries?
A battery is not a simple system. It's a number of components that are combined together that have to work synergetically to actually give the performance of a battery. What graphene can do is it can improve performances of each component of a battery. So if you're looking at storage capacity, graphene helps increase it. Looking at power delivery, graphene allows for a higher power output without increasing the resistive losses. It also helps reduce short circuits and dendrite growth, which is one of the biggest dangers of lithium-ion batteries, which can cause fires and thermal runaways. So without being specific, it can help every component of the battery.
Incorporating graphene into batteries may solve one of the biggest obstacles in the transition to greener modes of transport: electric vehicle range anxiety. This is the concern about how far the vehicle can travel between each charge.
One of the bigger drivers for energy research is being able to achieve the ranges that you can with internal combustion engine, that 600, 800,000 mile range. Graphene can help push that towards that in the short term, but in the long term it will also allow for the generation of
batteries that can achieve 1,000+ miles.
As well as the different application laboratories, the Geek offers facilities to scale up and test products at larger sizes.
So welcome to the Geek Pilot Hall. This is where we take our upscale activity. So we've been to see some of our laboratories where we go through the small scale to the 1 litre. We start to go into the more industrial scale applications. So as you can see, we've got a lot of kind of overhead cranes here, a lot of what we call company R&D.
How rare is it to have this amount of space dedicated to getting graphene out commercially?
It is very rare to have all the applications under one roof. So there's a number of applications that are in our application laboratories, but then to have a pilot hall, this allows us to de-risk what we call applications, de-risk scale. If you think of a company who then gets to a trial of 1 kilogram, 10 kilograms, 20 kilograms, they have then got to start to accelerate this into a production.
The Geek operates a partnership model at different tier levels, offering companies including small to medium enterprises access to a wide range of specialist resources to help bring their products to market. One such company is Vector Homes.
Vector Homes is really looking at two of the big challenges which our world faces today, so the climate crisis and housing inequality. We had this kind of shared vision around how graphene could be incorporated into some of these waste stream materials to produce something that is impacting us, our generation of people.
Take me through the steps in which graphene is being used in the production of the homes you're making. What
we're particularly interested in is looking at the elements of things like insulation or non-structural elements where we can make improvements in their efficiency, particularly around their thermal efficiency, but also looking at ways which we can do that where we reduce the embodied carbon that's associated with it. So we're looking at the whole life carbon of buildings. So graphene is generally found in the form of a powder or in sheets. We don't produce graphene, so we buy graphene in from suppliers like First Graphene, usually in the form not of powder but of something like what's called a master batch. So that would be a material like this where it's already been loaded into a carrier material. In this case, this is high density polyethylene. So there it is, it's safe. I'm fine to handle it with touch, and it's not airborne or anything like that. And then what we do is we then combine that with, in this case, things like post-consumer recycled plastic, combining them together with an extrusion process and producing materials in the form of pellets. These can then be formed into structures with injection molding or further extrusion processes, or even foaming processes as well. So we can produce a quite wide variety of structures that all contain that beginning graphene.
2024 is a big year for Vector Homes. They've just built a prototype of their affordable and modular home, which they plan to roll out later in the year.
What are the wider benefits of using graphene for the construction industry and for house building?
The critical thing for us is, one is the multifunctional aspects that it brings. So as a general statement, what we're trying to do is reduce the overall weight or the overall mass of construction. That's one of the primary ways that we can reduce its impact on the environment. So if we add in 0.5% or 1% of graphene material, but can we save 20 or 30% of the overall mass that we're adding, whether it's in foundations, in structures, in insulation, and then you build on top. So that gives you one benefit, but then if you build on top of that, that you can then potentially enhance its thermal resistance and so on, then you get this sort of multifunctional cascade effect that generates multiple benefits.
As well as in the construction industry, graphene shows much promise when it comes to membranes that can be used for water filtration and desalination, and also coatings which could be used for packaging and preventing rust. Many more 2D materials have been discovered and are under development, with single element materials such as boraphene, silicene, phosphorine and goldine. But there are also 2D materials made up of two elements. Jae-jong Byun is CEO of Nanoplexus, a company based at the Geek, developing the 2D material Maxine.
So we developed a material called Maxine. We've gone from sourcing the raw materials that are required to make it and become the leading manufacturers in the world at the moment.
And what is it?
So the simplest way to explain it is a variation of what people probably commonly know as graphene. So we mixed in a little bit of carbon-based compound material with a metallic. So what we end up getting is a powder like this that has very close to metallic properties.
The material is still in development, but potential uses include batteries and energy applications, and for smart textiles where the metallic properties can allow for sensory feedback.
The discovery of graphene has really set the platform for us to be able to develop new next generation materials. And graphene is still going to be one of that. I think it's a bit like in the kitchen where we have the rack of spices and herbs. I think it's going to be like that. So every different partners or industry members are going to have different needs. And it's going to be choosing that specific blend of whether that's graphene or MaxIn or blend of both that will allow us to be able to meet the criteria or the parameters that every industry partner is going to need.
The UK is not alone in developing graphene. The US and China have also invested heavily in the materials research, and China now produces the most globally. Recently, scientists from Tianjin University made a breakthrough, developing the world's first working graphene semiconductor. The team, led by Professor Ma Li, with help from researchers at Georgia Tech University, found the semiconductor about 10 times more effective than silicon when tested. 20 years on, it seems the graphene revolution is underway, with many exciting developments on the horizon. But perhaps a more accurate title is the 2D materials transformation.
It's really exciting to be working on this material that has the power to revolutionise electronics and to be some of the first people to put that to use in real-world devices.
What does the future hold for the work that you're doing here at Paragraf, and more widely, how graphene is being used?
Well, I think it is world changing because, biosensors can change the world of medicine, and the electronic devices here, the transistors we want to make, can change our world of computing. I mean, it really will make computers 2,000 times faster, but I think even more important than that, we know on the devices we're making here, we save 1,000 times the electricity. It's 1,000 times lower consumption. We think the transistors of other 2D materials which we haven't yet made will probably 100 times the lower energy consumption. That 100 times will make it almost negligible when you use your computer and so on. So I think, we're really optimistic because what we're doing here could be world changing, a huge advance.